Here we are at ANT03, lecture on radiation theory in antenna engineering. So what we're going to do today is learn about how to go from Maxwell's equations to solving what I like to call a class 1 radiation or antennas problem. And that is, you know what the antenna's radiating currents are. How do you translate that into radiated fields and circuit behavior? The other two class problems that we study in this class, the class 2 problems, are instead of having an estimate of the antenna's radiating currents, there's a certain class of antennas that you can estimate the nearby field distribution and use a sort of Huygens principles approach to project the field into the far field and figure out how the structure radiates. And the class 3 problem, of course, is you have to punt the football because there's no way to analytically solve it. You have this chicken and the egg problem where you need the currents to solve for the immediate fields, and you need the immediate fields to solve for the currents on the metallic structure that you call an antenna, and that requires numerical techniques. And of course these will be very, very important because most antennas nowadays are class 3 problems. To study them, they're too complicated to work out on pen and paper. However, you can glean a surprising amount of intuition from studying the first two types of antenna problems. And you can also double check the computer in class 3 with that kind of knowledge to figure out if the computer is lying to you, which it sometimes does. So building intuition in class 1 and class 2 problems are extremely important. Okay, so let's start with show and tell like we always like to do here at Antenna Engineering. Here I have a picture of an antenna type that called the half-wave dipole. We call it the half-wave dipole because this metal part here, which starts over here and goes all the way down to here, made out of some nice brass rod that some student found at a hobby shop or Home Depot or something like that. That length is 1/2 of the resonant wavelength of frequency. Now, one of the most important equations in the class we know is this equation right here, speed of light or velocity of propagation. Usually for antenna engineering, our speed of light is our velocity of propagation because our antennas are in free space or air. We know that that's equal to lambda times the frequency. For this type of antenna here that I have a picture of, this is about 1 foot long, about 30 centimeters. So that means that the wavelength here is about 0.6 meters or somewhere around 433 megahertz, which happens to be an ISM band, industrial, scientific, medical. That's an important acronym to learn in antenna engineering or anything related to RF, because these are unlicensed bands that, if you are observing the maximum power requirements and the certain antenna types, you may transmit whatever you want at any time in these without paying for it. This is very different from a licensed band, which is something you have to pay a lot of money for. You're paying for the privilege of excluding people from your spectrum, which is what the cellular carriers do. ISM bands are different. This is a particular antenna actually comes from the gigantic stockpile of fifth floor old senior design projects and research projects of yore from which Professor Durgan draws all of his show and tell examples. There have been so many activities here at Georgia Tech and so many antennas that it is actually pretty easy to find a show and tell for any given topic at any given antenna topic. So let's go. Ask the question, how do we figure out what the current distribution is on this device? And to do this, we're going to start with an open circuit again. Remember from last lecture, we said that an open circuit, of course, reflects whatever wave is incident upon it on the end. So if we were to put a source here, you would get a standing wave on this structure. If I was looking at the current distribution, of course, whatever's going on the top bar is going on at the bottom bar. It's the same current. It has to be a balanced transmission line structure if I have two pieces of wire here. However, we know that there's going to be a standing wave power pattern. At an open circuit, the current is zero at the end of the line. And then we know that it constructively interferes about a quarter of a wavelength from that end. And then a quarter of a wavelength later, you get a null. So 1/2 of a wavelength from the end, you get a current null, and the pattern repeats itself for as long as the transmission line is. This is something basic you learned in 3025. And what's interesting about this is that you can use it to estimate what this half-wave dipole is doing in terms of standing wave currents, because it turns out if you wanted to solve this as a class 3 problem, one way of doing that for a wire antenna is to solve some complicated system called Pocklington's integral equation. We're actually going to talk about this later in the class. But suffice it to say now, this is a difficult problem mathematically to do that. However, for wire antennas, one way to solve for Pocklington's integral equation is to contort the open circuit transmission line into this geometry of the wire antenna that you're looking at. And what do I mean by that? Let's take this, and we've got an open circuit antenna line, but I'm going to basically take back, if this is my open circuit, I'm going to cut this off at 1/4 wavelength. And of course, here's the bottom bar for the return current. I'm going to cut that also at 1/4 wavelength. And I am going to bend this back so that now I have the following structure. And if I just assume that the open circuit antenna, or the open circuit transmission line, is doing exactly the same thing in terms of its current distribution as it did when it was just a straight open circuit transmission line, I actually get a surprisingly good approximation to Pocklington's integral equation. And it'll take us a while to prove that, but suffice it to say now that what that means is that I'm going to have currents, a standing wave of current on this antenna, which is going to contribute to radiation. And then I'm going to have other currents here that do not contribute to radiation. Why? These are confined currents. In other words, if I've got a current this way, I've got the equal and opposite current right next to it on the transmission line so that there's not going to be any radiation from that structure. It's field confinement mostly between the antenna feed elements, the wire that feeds the top bar and then the bottom bar. This structure over here, however, is different. I don't have that destructive cancellation. Instead, these currents, when I bend these back, are doing the exact same thing in the exact same polarity. And so this is capable, this geometrical structure is capable of launching far field waves. Now, what does that distribution look like of current? I just take whatever I did for the open circuit and I just map it onto this new distorted structure. So I assume that there's very little distance between my top and bottom bar, such that this whole length is now lambda over 2. Lambda over 4 segment here, lambda over 4 segment here. I have zero current at the end, raising up to a maximum peak current of what we'll call basically I into the antenna. And same on this side. Zero at the end, peak at the middle, symmetrical. You'll notice that when I bend these two back from the open circuit configuration, that they're now all aligned. So really that the radiating part of the half-wave dipole is essentially a piece of metal in which a standing wave of current has a sinusoidal arc, 1/2 wavelength long. So back to this antenna here. We see that nice piece of metal here. Here's it's being fed to a coaxial cable. The inner conductor of the coax is soldered to one arm. We often call these arms of a dipole. And the ground plane is soldered to another. Now there's this really interesting structure here. Looks basically like a section of coaxial cable that has been glued to the side. It's actually electrically connected to the ground sheath on both ends. And what this is part of a balun structure. We're not going to talk about baluns yet, because it's a little bit too sophisticated for the first week of antennas class. But to give just a little bit of a preview to this, one of the things that can happen when you are taking an unbalanced structure, like a coaxial cable, and feeding a balanced structure, like a half-wave dipole, is that you can get unbalanced currents on the outside of the ground plane. This isn't something you normally talk about in transmission line theory. You assume that you have a coaxial cable that's fairly well behaved, where the inner conductor is always carrying the exact same current as the outer conductor. Now keep in mind that the outer conductor current is distributed across a much larger radius. But in theory, if this is operating the way a transmission line should, at any given point along this distance, even if you have standing waves, there's going to be the same peak current same current this way as this way. Just equal in amplitude, opposite in magnitude. Now, what happens in some instances when you feed balanced with unbalanced transmission lines, balanced antennas with unbalanced transmission lines, is that you get excess current, and unbalanced current on the outside of the transmission line, which means instead of just having a standing wave of current with a nice sinusoidal taper like we've discussed in our half-wave dipole, you get a lot of extra current flowing on the transmission line itself on the outside that contributes to radiation. This messes up your impedance of your antenna, how it behaves in a circuit, and it also messes up the radiation pattern and all the things that you were trying to do in a simple antenna like So, one of the things One of the reasons why you have this quarter wavelength balun on here is to suppress those currents that are flowing on the outside of the coaxial cable. Now, the astute student will look at this system and say, hey, wait a second. You said this is a quarter wavelength. Look at that. This is a picture taken directly overhead on my carpet of this half-wave dipole. This arm is a quarter wavelength. And I said that this is also a quarter wavelength. But wait a second. This is clearly longer than this dimension here. And that's not surprising because it's really the dimension of the wave in medium. Remember, a coaxial cable is filled with dielectric of a permittivity of somewhere between 2 and 3. So the wavelength is going to be the square root of 2 or the square root of 3 smaller than in free space. So we should not be surprised to see that this quarter wavelength balun is shorter than the quarter wavelength free space arm of these two dipole arms. You'll also know that there's some notice that there's some black tape here, and there's also some wood here and a wood dowel here. These are things that are essentially invisible to RF. When they're electromagnetically small, they don't even influence the propagation much or the antenna performance, and they're used just for mechanical stabilization. This is clearly the work of a practical engineer who did a good job at whatever senior design project 20 years ago that they attempted with this device. So we'll be talking more about half-wave dipoles and how to solve for them in a later lecture. So let's talk now about the radiation equation and how to actually mathematically solve these class 1 radiation problems. These slides you can find online. And we're going to start with the Helmholtz wave equation. Now, if you've gotten this far in the antennas course, hopefully you've reviewed the Helmholtz wave equation lectures and the Maxwell's equations lectures to figure out our starting point for today. So what I have here are two of Maxwell's equations. Let's get the pen ready. This one is basically Faraday's law, and oh my goodness, I'm writing in bulldog red. Let's stop that nonsense right now. And excuse me, this is Faraday's law. And this is a form of the corrected Ampere's law that Maxwell came up with. It says the curl of the magnetic field phasor, and that's what this squiggle is on top of each of these structures, each of these variables. The curl of the H field is equal to the time derivative of the E field plus the current density. Remember, this is current density in amps per meter squared. And what this basically means is H, the magnetic field, circulates. If I have a current, H field circulates according to a right-hand rule around a current, or in this case, it's a volume distribution of current that has amps per meter squared. And it also circulates around changing E field. So if there's an changing E field in here back and forth, you will also circulate a magnetic field. Faraday's law, on the other hand, says that E field circulates around a changing H field. This minus J2 pi f in the frequency domain for a phasor. The astute student will instantly recognize this as the time domain equivalent of the time derivative. Likewise up here, time derivative. of a sinusoidal wave. So if I change h, I will change e. And if I change e, I will change h. And if I change h, I will change e. And look at this. We have a chain reaction that causes propagation. And this is really the takeaway from the lecture on the Helmholtz equation. That you have this marvelous coupling of E and H that causes the propagation of electromagnetic waves in space. And in the Helmholtz wave equation, we were simply studying waves in free space. There was no J term. Why? Because to get this form of Maxwell's equations, we needed a simple medium which was linear, isotropic, that means it behaves the same in all directions, and homogeneous, which means the same in every point in space. We also needed a medium that was source-free, which means there were no charges in the medium, nor was there current density or anything quite like that. And so charge and current were zero for the Helmholtz equation. So this was Helmholtz. And this is all discussed, the Maxwell's equations that are discussed in WAV Module 1, and Helmholtz is discussed in WAV Module 2. Now here's the problem. If we use the Helmholtz wave equation, we can study how waves propagate in space, but we can't really understand how antennas behave. And why is that? Because we got rid of the sources. An antenna, by definition, has to be a source. So we are throwing the baby out with the bathwater if we are doing things that way. So in order to fix this, of course, one of the problems, let me clear up my mess here that I made of my one of the problems that we have is that we don't get a really nice, good mathematical behavior when we leave this term in. Because you remember from the Helmholtz wave equation, when I derived that equation in the previous lecture, I took the curl of H and then I took the curl of it again. And that allowed me to take the curl of E on this side and plug this straight into here. And then I had a beautiful thing that had only curls of H's. But if I leave this J term in, I'm going to have a curl of a J, which is really challenging to work with mathematically. And so we have to come up with an alternate system. It doesn't lead to a really, if I do it the old way, it doesn't lead to a really nice, clean solution. And so the way to do this is to introduce this quantity, which many of you may have never seen before. It's called the vector magnetic potential. We usually represent that with an A phasor vector in electromagnetics. And the A phasor vector, if you take the curl and divide by the permeability, gives you the magnetic field. And I always liken that to the analogy of the scalar electric potential that you learned in 3025 or undergraduate electromagnetics. In this case, we have a scalar electric potential, and we should make that a phasor, put a squiggle on top, is equal to minus the gradient. E field is minus the gradient of the scalar electric potential. So this is a scalar function of 3D space. You take the gradient, you put a minus sign in it, in front of it, and that gives you the E field. And so this, of course, has units of volts and is a very convenient way to characterize the E field in three-dimensional space. Likewise, this A vector is a very convenient way to characterize the H field in three-dimensional space, you just take the curl of it, divide by 1 over mu. And it turns out that using this helper variable, because that's all this really is, a helper variable, you can solve the radiation problem in a much simpler form. In fact, what we'll find is that if you use A, you get something that looks almost like the scalar wave equation or the Helmholtz wave equation in terms of A instead of terms of E and H, which is impossible. So let's start with this first Maxwell's equation and apply these definitions that we learned. Here is Faraday's law, which says that electric field circulates around a changing H field. So this is my H field. It's a phasor vector. It's oscillating back and forth. I'm going to get an E field that circulates around that, according to this Maxwell equation. By definition, if we plug this in here, we find that E must be equal to minus J 2 pi Fa, where this is our vector magnetic potential. Now, why is that? Look at this. I've got a curl of E is equal to all this stuff minus J 2 pi F. This is a constant. These are all constants, not functions of space. So I can take them out of the curl here, or I could move them in. It wouldn't really matter. And then I have the curl of A. And this means, of course, that if the curl of a three-dimensional vector function is always equal to the curl of a three-dimensional vector function, then those functions must be effectively equal. And that's what this part of the equation says. Except I am allowed to add any function here that can be expressed as the gradient of a scalar. Now, why is that? Because if I take the curl of both sides of these, I get the equation up here on the left-hand side, and of course the curl of any gradient of a scalar function is equal to 0. So this involves a basic vector calculus property that I liken to just simple integration and differentiation. If I have a function v of t, and I have a function u of t, and I have an equation that says the derivatives of those must be equal, then I know that v of t equals u of t, except there might be a constant difference because the time derivative of the constant is 0. As long as the time derivative of the constant is 0, then I could add whatever c I want to this system and still make this original differential equation hold. So really, what I'm talking about down here is the simple form, basically an analogy to this simple differential equation behavior that I've outlined up there. We're just using slightly more complicated vector identities. Now, okay, now let's go and take a look at this second Maxwell's equation. We know that H is really the curl of A, phasor vector, divided by the permeability of the medium that you're operating in, according to that definition of vector magnetic potential. That means that we can write this as J2 pi F epsilon times E, the E field, plus any sort of current density form that we have in there. Now you remember that the E field, according to the other Maxwell's equation that we manipulated, takes that form. So if I take this and substitute it in for the E field, I get this equation right here, which looks like a monster, right? I'm going to try to simplify this by applying a vector calculus identity, which says that the curl of a vector A, of any vector A, is really equal to the curl of the divergence of that vector, there should be a vector sign on top of that, minus the Laplacian of that vector. Now, this is almost identical to a relationship that we used in deriving the Helmholtz wave equation. And this is the same thing. It's purely mathematical. You can go and write these operations out longhand in terms of different partial differentials, operators with respect to x, y, and z. You'll get a monster expression on the left-hand side, and then you'll get this really ugly expression on the right-hand side when you do all these operations. And lo and behold, when you simplify, it will be the same thing. It's very difficult to imagine from a conceptual point of view. I always tell my undergraduate engineers that the curl of a vector tells you its swirliness, how it swirls around. So what is swirliness of swirliness? Double curl. It's very difficult to visualize. Divergence, we kind of understand that. Remember that the upside down triangle, the nabla, is partial derivative with respect to x on the x hat unit vector, partial derivative with respect to y on the y hat unit vector, partial derivative with respect to z on the z hat unit vector. We're dotting it with a vector to take the divergence, and then that takes a vector and gives us a scalar quantity, which then turns back into a vector when I take the gradient operator, basically this thing distributed across that scalar. So this gives me a vector, and then I have this Laplacian, which we know from our previous lectures is the shorthand for the divergence of the gradient of something. Now normally in your undergraduate classes you would put a scalar function of three-dimensional space there, like voltage, for example. X, Y, Z. That's a function of three-dimensional space, but it is itself a scalar function. You would take the gradient, that would give you a vector. Then you take the divergence of that vector, that gives you back a scalar quantity. And you may have solved Laplace's equation, which basically says that in the absence of charge, the Laplacian of V is equal to 0. And you can solve all sorts of interesting field problems that way, using Laplace's equation or Poisson's equation, when you have 0 there as the boundary condition. Now, that's all nice, but what I have here is the Laplacian of a vector. And all that really means, when I take the Laplacian of a vector phasor, or any vector, that really just means that I'm taking the Laplacian of the x component of that vector that sits on the x hat component, plus the Laplacian of the y component of that vector, and I'm keeping it on the y hat unit vector, plus the Laplacian of the z component of that vector, and I stick that resultant on the z hat unit vector. So, all that to say, let me go ahead and erase and start from a clean slate. All that to say is this is just a purely mathematical identity. If you understand the way that these operators are written and you do it out longhand, you can show that it holds for any vector mathematically, regardless of what that value actually is in A, whether it's the vector magnetic potential or a vector field denoting people traffic in a certain area, or whatever physical quantity you have here. Now, switch to green. It'll be fun. What do we have when we do this? We basically take curl, double curl of A, stick this relationship into here, and that allows us, okay, first of all, you'll notice on the second line, we've distributed the mu on both sides, and we've distributed this constant through our replacement for the E vector phasor. Then when we stick this over into here, this relationship into here, what we find when we rearrange terms is this complicated expression with respect to A. This part over here looks exactly like the Helmholtz wave equation. We have the Laplacian of A, our vector magnetic potential, plus a constant, the wave number, which is 2 pi over lambda. So k squared is actually 2 pi over lambda quantity squared. So we have this, and that must be equal to minus mu times the current source. So remember, this is the input to our class 1 antenna problem. This is the oscillating current in space. If you know what the oscillating current in space is, then you can solve for the vector magnetic potential. And if you know what the vector magnetic potential is, you can then figure out through these relationships here, basically this, and then this subsequent relationship, solve for H, and then solve for E. So it's a two-step process. But the problem is, it doesn't look like we've made as much headway in this system as you would think, because we've applied a bunch of vector calculus identities, and we've managed to make the problem apparently more difficult than what we started with. Laplacian plus k squared on the vector magnetic potential minus all this stuff is equal to the current. But we have an ace up our sleeves, and that's where this gauge condition comes in. Okay. So if we go back to the beginning here, where we define the vector magnetic potential. There's a theorem in vector calculus that says to completely describe a vector field, we need to do two things. We need to describe the curl of that vector field, and we also need to describe the divergence of that field to completely pin down the vector field as a function of x, y, and z, three-dimensional space that also is a field quantity at all these points. We need those two pieces of information. And that's very interesting because, in a way, we have only partially defined our vector magnetic potential, a vector, by saying its curl must be equal to A. So this means really is that if we know what the H field is, there are actually an infinite number of A vectors that can be taken the curl of and still make an H vector that we desire. Only by also specifying the divergence of that field can we pin down a unique A that we can carry forth in our equations. And we're going to use that fact because the gauge condition here, remember, we've specified what the curl is, but we have not specified what the A field is, the divergence of the A field is. If we say the divergence of A is equal to minus all these constants times the scalar electric potential, that means this entire complicated term goes to zero. And what we're left with is a beautiful scalar wave equation, not with respect to electric field or magnetic field, but with respect to our vector magnetic potential. So by introducing this helper variable, the vector magnetic potential, we can use all the math and all the simplifications that are used to solve the scalar wave equation, which now, instead of equal to 0, is equal to our source, J, straight up without any modification other than this little minus mu constant. And then once we have A, we know we can take the curl of that field, divide by mu, and get the magnetic potential, or the magnetic field, excuse me. And once we have that, we can use Maxwell's equation to take the curl again and get the E field by Ampere's law. So that's our two-step process. Step 1, solve for A, vector magnetic potential. Step 2, A, solve for H. Step 2B, solve for E, which follow with standard definitions from A. If I try to solve H and E directly, given just the current function J, that's problematic. That requires something called a dyadic Green's function. Which is beyond the scope of what we're going to talk about in antenna engineering. But needless to say, it is quite nasty. It is not a scalar wave equation. Scalar in the sense that if I have an x component of J, then that's going to lead directly to an x component on a sub x phasor. And the y components of J result in y components of A, and the z components of J are the only things that result in z components of A. That's the simple scalar wave equation behavior that we're going for in our mathematics to make the solver simple. And then once we have A, we get into E and H, because E and H do not simply relate to the x, y, and z components of J in a scalar fashion. That's why we call it the scalar wave equation, even though there are clearly vectors in this equation. So, Green's theorem for solving the scalar wave equation. Basically, let's say, hypothetically, that the vector magnetic potential that we're solving for, first of all, only has a z component, which means we are only considering z-directed sources, z components of our current density, because that's what produces z components of A. Without loss of generality, that's a perfectly fine simplification to make, because this is a linear system and it's a scalar wave equation. If I want to solve for the x component of J, then I effectively just tilt the world 90 degrees and use the exact same mathematics for that and get A sub x. And if I want the y component of J and see how that influences radiation, I solve for A sub y by tilting the world 90 degrees in the other direction. And I effectively take a 3D problem like this and turn it into 3 separate linear problems that can be added together in any combination that I want to solve for an arbitrary J vector. which results in some sort of A vector that is similarly aligned. So, this is just operating on the z component of A without loss of generality. And I'm going to exclude the current source everywhere except for the origin. So on the origin, I could put, conceivably, a little delta of current, the delta function. Delta sub z, or operating on z. I'm going to stick that on the z hat direction, and I'm going to make a little current element I. Just a little smidge of current at the origin, nowhere else. It's actually a non-physical situation because currents have to take up space. How can currents be oscillating back and forth in zero space if there's no current here or no current there? I'd have charges building up ex nihilo, which is inappropriate. But if I exclude just the origin, I can solve this. I actually have two very simple solutions that solve this equation. One of them is any constant c sub 1 times exp to the minus jkr, where k, of course, is the wave number. And we're solving this now in the spherical coordinate system, where r is the distance away from the origin that you travel. What does this mathematically describe? It's a traveling sinusoidal wave that falls off 1 over r in amplitude as I move away from the origin. And there is a minus jkr linear phase taper. Whenever you see exp minus jkr with a linear phase taper, you know that that is constant velocity traveling wave propagation of a sinusoid in the phasor domain, and it's in the positive direction of whatever this vector or scalar variable is. In the case of r, that means that this wave is traveling at a constant velocity away from the origin. The phase progresses proportional to the distance from the origin. So I've got a traveling wave that emanates from the origin and falls off 1 over r in amplitude. There's a second solution that is almost identical to that, except for the sign is reversed, and that basically is a collapsing wave. A wave that starts off in infinity and collapses to a point. These are sort of the two complementary solutions with different constants that you could add in different proportionalities and solve this equation. Now, we don't care about this solution here, the second one, because it's a non-physical solution. Can you take a boundary condition off at infinity and make a wave collapse precisely at a point at a constant velocity? Mathematically, yes, that would solve Maxwell's equations. Realistically, you would have to be a supreme deity to make that wave propagate. And so we have always, since the beginning of time, assumed that that is not something that would physically happen. And so we just look at the wave that propagates from that little element in the origin. And if that's the case, we can apply Green's theorem, which says here's the propagating term for that source at the origin. And here's a general distribution, a volumetric distribution of current. So R is the distance between that volumetric current distribution and the point of observation. And here's a very critical difference now. When we start talking about distributions of current density, J vector, and keep in mind the way that I've drawn this, or the way that we've assumed this should all be z-directed pointing. But the amplitude and the phase can vary with respect to space. Now to do that, we are going to have to take that basic kernel and apply Green's theorem and move that around all the entire volume. So by doing that, we can superimpose all the contributions and figure out what is A sub z at the point of observation x, y, z. So because these problems get a little bit hairy, I adopt this following notation. X, y, and z, without any adornment or primes or subscripts, denote the point of observation. And that's contrasted with x prime, y prime, and z prime, which I need to slide around under the integral operator as my variable of integration. So I've got a current distribution J. I have to slide around here and superimpose all of the contributions with the three-dimensional integral to figure out what is my A field out here at x, y, z. That's my point of observation. If I change the point of observation, if I move over here, I got to repeat this integral all over again, now changing x, y, and z in this variable here to recompute. This is one of the reasons why electromagnetic computation is so difficult and time-consuming, even for a computer. And that's because really this is a six-dimensional problem. If I have a radiating system with J sub z, and I need to calculate a field map, I basically have to digitize the universe and sample it, and every sample point results in another integration of this body that itself must be sampled. And so we're almost looking at like a six-dimensional problem. X, y, and z are three dimensions for your point of observation. X prime, y prime, z prime are where you're integrating the currents. And you need to take every single one of those into account to figure out the amplitude and phase at that one single location in space. Change it a little bit, you change your R, and you have to recalculate this whole thing. So this explains the complexity and difficulties in numerical electromagnetics, even for something relatively simple like this. So if we define these helper variables, R and R prime vector, that have the points of observation and the variables of integration, I can write my z component vector magnetic potential in the form of this basic volume integral, where I integrate J sub z with this Green's function kernel with respect to x, y, and z. And that's it. That's where we'll stand up. This is the key result from our lecture. What we're going to do in the next lecture is to go through and take a look at the simplest possible solution for this, which is the Hertzian dipole. That's where basically I only keep this J as a little delta function of current at the origin, oriented in the z direction. So I get z component vector magnetic potential. This is the simplest radiation system we could possibly conceive of in antenna engineering, and it turns out the solution is actually really complicated. But it's important to work through because you'll be able to see where we make approximations, such as the far field approximation in electromagnetics. That greatly simplifies our antenna problems, and we'll be able to take that simplification for the rest of the course, essentially, to study realistic antennas.